Okay, hello everybody. And so they were here on Friday. It's been a long week, and hopefully we'll be able to kick into chapter 9 next on Monday. Okay, we're going to finish up chapter 8 today, which is alkenes and alkynes and their reactions. So what I've decided to do for the rest of the semester is actually move homework from being due on Friday at midnight to being due at Monday on midnight. So you have the weekend to work on it and spend a little more time, doing your reading assignment and catching up. So all of those have been moved to Friday. All of the assignments on Canvas, if you follow Canvas to do your assignments, those have all been updated and are correct as well. Okay, so but the schedule, the schedule of classes and assignments has not been updated yet. I'm hoping to get those updated over the weekend. So I just wanted to update you on that. I think some people were kind of asking if they could do it over the weekend because of jobs and stuff like that. So I thought, hey, let's do this. Okay, so we're going to finish up module 8. And so we're going to finish alkenes today, and then we're going to do alkynes today as well. And then we're going to start module 9, which is spectroscopy on Monday. Let's see, and that's all the administration I have. Does anybody have any questions about that?
I actually had a quick announcement about SI.
Okay.
I was misinformed. I thought that today was the last session you could get credit for. It's actually Monday. For some reason, it's actually Monday. So if you go attend session on Monday, that will be your last opportunity to get credit for a session. I think that was because of actually, what was that holiday that was on Monday?
Yeah, we had Labor Day and
Labor Day, I think. So that's why. So if you attend session on Monday, you can get your credit on the exam. But yeah, sorry about that.
Good to know. All right, let me go ahead and pull up my slides and let's get into this. If you have any questions, of course, chime in. I think the video that you saw, the audio is working really well. I got to hear Nicholas give his announcement very clearly. So I hopefully have that fixed so you can actually start asking questions. All right, let's go ahead and share my screen, put my module up there. And okay, come on, let me move it. All right, there we go. So we were talking about this module 8 right here. And of course, we've completed most of this. And we were looking at specifically the oxidation of an alkene with osmium tetroxide. And the cool thing about this, and the cool thing about all these reactions, and when you go back and study these reactions and try to rack and stack them, look for the reagent and whether it's syn addition or anti-addition, and whether it follows Markovnikov's rule. So the stereochemistry and not necessarily stereochemistry, but the regiochemistry. The regiochemistry, each of these different reactions has a different type of regiochemistry, and a lot of times it's explained by the mechanism. For example, if it forms a carbocation, it's going to follow Markovnikov's rule. If it has some kind of bridge structure, like in the osmium tetroxide here, that means it's not going to go through a carbocation, and therefore selectivity and regioselectivity is designed by that intermediate. So keep in mind when you're going through this and studying that those are the kinds of things you want to look for, and start drawing some analogies and saying, oh, this set of reactions is like this set of reactions. Okay. So we said that we could do the osmium tetroxide with just a catalytic amount of osmium tetroxide because it's highly toxic, and we could just continuously oxidize the osmium, but it still gives us that cis diol, the 1,2 diol in all of these systems, because both of the oxygens are transferred at the exact same time on the same side of the alkene. Okay, so there is another thing we can use here, and it's called permanganate, and it's either potassium or sodium permanganate. Unfortunately, it's a stronger oxidizing agent, and while you can get this syn dihydroxylation, just like with the osmium tetroxide, you can only do it under very cold conditions. It has to be in like ice bath. If it's not an ice bath, if you do it at room temperature, it's kind of autocatalytically heating, and what can happen is instead of giving you the diol, you actually cleave the alkene completely, giving you carboxylic acids. Okay, so that is one of those reactions where, again, selectivity of reagent is very important on the product you want. And what we're going to see here is this potassium permanganate has a different kind of reactivity when we look at alkynes toward the end of today's lecture. Okay. The next kind of reaction we have is what we call cleavage, oxidative cleavage, okay? So we're actually gonna break where the double bond is, and it's very selective. It uses that electron-rich double bond as the location where it's going to react, and you actually break that double bond, creating two carbonyl compounds. So you can make aldehydes or ketones from it, or carboxylic acids, depending on how you do it. If you work it up where you don't have an oxidizing agent like a peroxide, you can actually stop at aldehydes and ketones. And this reagent we selectively use is called dimethyl sulfide. And what we're going to end up doing is transferring one of those oxygens of ozone to the sulfur and the other two oxygens of the ozone to the alkene. Okay. However, if we do an oxidative thing, that aldehyde is going to oxidize down to a carboxylic acid. So one of the cool things about ozone is, it's a stable molecule, but it's very reactive. And it's very reactive because we have, if you look at its resonance structure, it has a positive charge on one side and a negative charge on the other side, which means it acts as, it's what we call a 1,3 dipole reagent, meaning it can attack using both the anion and the cation at the same time to create these reactivity. So it acts as a nucleophile, it acts as an electrophile. That's why it's so reactive. Okay. So when we have this ozone come up and look at this electron-rich alkene, the first thing that's going to happen is do a 1,3 dipolar addition, meaning that it's going to have all three atoms add across that double bond, giving this 5-membered intermediate. Excuse me. So my allergist has me off all allergy medications so they can do allergy testing. So I'm going to get worse before I get better. All right. So when we do this dipolar addition, we have this nice little 5-membered ring, and then it typically rearranges to give us this other 5-membered ring right here. Okay. Now this is a little bit more stable. And so it kind of rearranges itself to give us this compound here. But if it doesn't rearrange, it actually will undergo a reverse 1,3 dipolar addition, yielding a ketone and an oxidized species here. So this would be like a per alcohol. It has an extra oxygen on it, so it can do that as well. But in this case right here, shrink. There we go. All right. The typical reaction is where we add ozone across an alkene, okay, and then we react it with some kind of a reducing agent. So in the case of the dimethyl sulfide, the sulfur is actually the part that gets the extra oxygen. Or in the case, we can actually use zinc metal, and zinc metal will also take away that extra oxygen in the system, giving us our final products. So let's take a look at a tri-substituted alkene. In a tri-substituted alkene, we'll get, again, insertion into this double bond, giving us our intermediate here, okay? Now, we've gone from our sp2 hybridized carbons to our sp3 hybridized carbons, and in that right there, that actually, it's fairly stable. You can isolate it, but most of the time, we just decompose it with our zinc and our sulfur, and the di-substituted side becomes a ketone. But the mono-substituted side does not oxidize off this hydrogen, and we actually end up with our aldehyde. And of course, that remaining oxygen is transferred to one of these two other species here. Okay, so in this case, we have a way to stop at the aldehyde. Okay, now, if we have a di-substituted and they're di-substituted on the same side, we still produce a ketone, because notice that you're clipping it here in the middle. And so this side stays a ketone, and this side becomes a dialdehyde, or in this case, a formaldehyde right here. But again, only if we're working it up with this reductive workup, okay? If we do hydrogen peroxide, that's an oxidative workup, and that's going to oxidize the products down to their most stable form. So in the case of this tri-substituted, instead of forming an aldehyde and a ketone like we did above here, we end up doing something different, okay? So in theory, we generate this intermediate here as well, and we do generate that aldehyde, but in the process of this oxidative workup, that aldehyde is oxidized down to a carboxylic acid. But the ketone is very stable to oxidation, and therefore the ketone does stay. And notice the carboxylic is more oxidized than the ketone, but we had to have a hydrogen attached to that carbon to do it. Now, that being said, what if you had a tetrasubstituted alkene? What do you make? Well, you only have one option. You're going to make two ketones. And if it's a symmetrical tetrasubstituted alkene, you're going to make two equivalents of the same ketone. Okay, so that you can make a whole bunch of one thing from two molecules from one molecule and have them be the same thing if it's symmetrical. Okay, so that's really neat because the ozone does not attack sp3 hybridized carbons because it has to do that dipolar addition, use those electrons in the alkene. So it selectively cuts the alkene apart. And it also reacts with acetylenes, and we'll show you that in a minute. Okay. So one thing to think about is strategy about how to use ozonolysis to generate the things you want to generate. So let's say, for example, you wanted a very complex ketone, but you didn't have one. And what you had was an alkene that you already made from some other different reaction right here. And so when we think about the products we're going to get from an oxidation ozonolysis of an alkene, you have to think of just cutting this right here and adding an oxygen to each side of that. And that's going to be your final product if you are using a reducing workup. So if you use that reducing workup, you're going to end up with a ketone on one side. And because it was a tri-substituted, you end up with an aldehyde on the other. Okay. Now, let's say you didn't want the aldehyde. You actually only want the ketone and you want it really easy to work up. Well, then you use an oxidative system and it'll convert the other compound to a carboxylic acid, which then all you have to do is add a little base in your workup and the carboxylic acid turns into a salt and is water soluble. Your ketone would be water insoluble and you could easily isolate it. Okay, but again, the strategy is the same. You basically cut in the middle there, add an oxygen to each side, and that gives you your final products. But in an oxidative workup, again, you oxidize your aldehyde to your carboxylic acid. Okay, so up to now, when we added HBr across a double bond, it went by Markovnikov's rules because the hydrogen was adding to the least substituted side. However, if we change the mechanism of the reaction to not form a carbocation, then we can change the selectivity or the regioselectivity of where the bromine adds. And we do this by changing the mechanism. Instead of being a nucleophilic electrophilic reaction, we're going to turn it into a radical reaction. And a radical reaction has some different aspects to it. We're going to learn a lot more about radicals in chapter 10. But I'm going to introduce the topic here. So when we have a radical reaction, we typically use something called a peroxide. It's basically an alcohol that you take the hydrogens off and you make an oxygen-oxygen bond. So the simplest one we know of is the hydrogen peroxide, which we just used in the last reaction. But we can use a lot of other organic soluble peroxides in these reactions as well. So if we just take any alcohol, we can oxidize it to give us this peroxide. So the cool thing about peroxide is this is a non-polar bond here. And because both oxygens have the same electron affinity, it's not going to pull both electrons to either oxygen. And so what we end up doing is breaking the bond homolytically and giving us one electron on each oxygen. Okay, so we're changing the mechanism by going from a nucleophilic electrophilic attack to a radical single electron attack. Okay, so once we do this, once we take that radical and break it apart and turn it into that, we now have changed the hybridization at the carbon. When it was bound to the thing, it was an sp3 hybridized, and so it was tetrahedral in electronic state. But now that we've broken that off, we've actually changed hybridization to sp2, okay? And like the carbocation, which is also sp2, we have that p orbital above and below the plane. In the carbocation, that p orbital is empty, and so we have a perfectly flat trigonal planar system. In the radical, we actually have one electron in that p orbital. And so it's sort of kind of trying to be tetrahedral because of that one electron is doing that electron-electron repulsion. So it's more pyramidal than a carbocation is, but not as pyramidal as a true sp3 hybridized carbon. And then if we add another electron to make an anion, and we'll look at those in a little while too, we actually get an even more, that we have two electrons adding repulsion, and we actually have it bent down to even beyond where we would see an sp3 hybridized carbon at 109.5 degrees. That being said, that shape of this radical having this electron in a p orbital controls the stereochemistry and the regiochemistry of this reaction. Once we form a radical here, just by creating this system here, it actually can, through space, be stabilized by this having a hydrogen next to it. And what can happen is that we can actually have a, in the case of a carbocation, we can actually have a hydride shift to give a more stable carbocation. However, in the case of this, we're actually stabilizing that radical, and so they don't really move, okay? So we do not rearrange radicals to give our system. Unlike carbocations, they do not do a hydride shift because we're actually moving one electron at a time, then we'd have to move another radical. So they do not move, okay? So now that we know a little bit about radicals, and we know it's an sp2 hybridized orbital with a single electron in it, why does that still control the regiochemistry and make it do an anti-Markovnikov addition? Okay, so to do that, we have to look at the different steps of the reaction. So in radical reactions, because you're dealing with a single electron, you don't actually just do a single attack and then it's done. You tend to do what we call a three-step mechanism. So the first step in the mechanism is initiation, the creation of your first radical. Okay, so initiation is when you take your peroxide and with heat or light, break it apart to give you a radical to start the reaction with. Okay, once you have a radical, then you need to generate the radical that's actually going to do the attack on the alkene. So in the case of this, you would attack HBr, because that's what we added into our reaction, with the radical to generate alcohol plus a bromine radical. Okay, so now that we have the bromine radical is going to come up to that alkene and say, hey, I already have one electron. I only need one electron of this alkene to generate our bond, right? So we have two options here. So the idea is the bromine already has one electron, and notice these arrows have only one barb in it. Remember that one barb in there means we're moving one electron, two barbs is we're moving two electrons. Okay, so we have an option where it can move one electron from the double bond over to make a new sigma bond with the bromine, and that would leave a radical at one site. Okay, and so that would give us a tertiary radical. Now, if we did this where we put the, had the bromine come in here and use one of its electrons to make that sigma bond, but then the other electron went to the less substituted side, that would generate a primary radical. Okay, just like carbocations, radicals have the same stability trend. A tertiary radical's greater stability is more stable than a secondary, which is more stable than a primary. So that means in the process of propagation, we're going to try to create a tertiary radical, okay? Which means this is going to happen much, much more than this happens here. So, but because unlike the carbocation things, they do not rearrange. Okay. So once we generate this radical here can then actually react with another system. I'm sorry, not this radical. This makes it, this is the more common one because it is the tertiary radical. It's the more stable. What we can have happen is we can have that radical, come on, move. There we go. That radical can react with another equivalent of HBr and move the hydrogen to this side here to give us our final product, our anti-Markovnikov product. Remember, the whole reason the bromine went here is to get that more stable tertiary radical. Okay. The other thing that can happen is now that we've generated another bromine radical, it can actually come and react with another alkene. And so every time you form your final product with no radicals in it, you've also formed a new radical that can go and react. So the reactions just keep going and going and going with that, just that small introduction of that free radical until you somehow take away that radical. Okay. And when we take away that radical and terminate it so that there are no more radicals in the system, that's called the termination step. Okay. And there's a couple different ways we can do our termination step. One termination step would be to have a bromine radical that you just created over here in your step react with the radical on the tertiary radical. It creates a product we don't want. It's a dibromo compound, but it would stop the reaction. The other thing that can happen is we can actually have two bromines react with each other to make bromine 2. And the other thing that can happen is we can actually have two of these carbon radicals react with each other to quench the reaction also. Okay, so what typically happens in these, we initiate the reaction, it keeps going through these propagation steps, until we have very little radical left. And at the last step, like there, when we only have, all the other alkenes have reacted and all we have is these radicals, we start getting these termination steps as minor products. But the key here is that because we are adding the bromine to the least substituted side, it is an anti-Markovnikov addition. Okay. So in review, we had a lot of different reactions, and the things to pay attention to are when we add, we need to pay attention to what we're adding. And so if we're adding HCl, we're going to get an H on one side and a Cl on the other. Okay. And because we're going through a carbocation intermediate, we get both syn and anti-addition. Okay. Because it'll add to the top or the bottom of that carbocation. In hydrolysis, we do the same thing. We add an OH to one side and a hydrogen to the other side. And again, we go through a carbocation intermediate. So we have syn and anti-addition. In halogenation, we form that three-membered ring, which blocks one side of the ring. So it has to come in the other side, which means it must be anti-addition. Okay. In the halohydrin reaction, it's the same intermediate where we had the halogen form first, but then we had a lot of water there to act as our nucleophile. And so we get a halogen on one carbon and an OH on the other to give us our anti-addition. Again, it's about the mechanism. Correlate the mechanism to the regioselectivity of the product. In the hydroboration, we get the hydroxide on the least substituted carbon. That's the important part about this one. And it's always a syn addition because it happens where we have that four-membered intermediate where the boron and the hydrogen add across the double bond in that four-membered transition state. And in our mercurization here, we have mercury on the one side, but it has a polarized bond. And so we have predominantly anti-addition, but we do have some syn addition in the system. With the osmium, we always have the syn addition. They're always right next to each other at the same time. We can reduce this down. That's also syn addition. But if we use a lot of permanganate and heat, it actually cleaves that double bond. And we can also cleave that double bond using ozonolysis to give us aldehydes, ketones, and if we have an oxidative workup, we can make carboxylic acids. All right, questions about alkenes? Okay, well, while you're formulating your question, I'm going to go ahead and pull up my alkynes slides. We only have 20 of these, so a lot of the same reactions happen this way, but they're slightly different. Alkynes, of course, just have a second pi bond, which means they are electron rich. And so many of the reactions react the exact same way, at least in the first reaction, because we're just adding across that double bond, a triple bond. Okay, but it has a couple different reactions we don't have in the alkenes. And one of the first things we have in the alkenes that we don't, alkynes that we don't have in the alkenes, is we have this acidic hydrogen. Remember when we talked about acid and base, the alkyne was the most acidic hydrocarbon, then the alkene, and then the alkane. And the alkanes were very, very hard to remove that hydrogen. But the alkynes were acidic enough to be taken off with a strong base, like amide and any anion made from an alkene. Sorry, alkane. So if we have something like butyl lithium here, that's a strong enough base to deprotonate this. If we have amide, which is N2 with a negative charge here, that's a strong enough base to remove that proton. And when we remove that proton, we actually generate a nucleophile. Okay. So one of the reasons it can form this, is so much more acidic, is the idea that it has sp2, it has sp hybridization. Okay, that sp hybridization changes the amount of S character we have in our system. Okay, so let's look at that. If we deprotonated an alkane right here, we have an sp3 hybridized carbon with an anion here. So both of those electrons are in that sp3 hybridized orbital, which means we have about 25% S character and about 75% P character. Okay, this is not as stable as if we have more S carrier. The more S character we have, the more spherical that anion is, the more stable that anion is. So if we go to our alkene, and we know we have an sp2 hybridized carbon, in this case here, we only have 2 parts p orbital, 1 part s orbital, and that means it has more S character, and therefore it's actually more acidic than the alkane. So if we look at our pKa's, they're very different here. But now when we go to our sp hybridized here, it's half S, half p orbital character, and that gives us the most stable anion we can form on a carbon system. Okay, so this will happen with any strong base to give us our nice acetylide ion. Okay, so how do we use this in the lab? Well, the 2 most common ways to make this acetylide ion is to use sodium amide in the presence of ammonia. That's actually used as a solvent because this dissolves very well in it, and the acetylenes tend to do that. And because this is a polar protic solvent, it supports our charge here. It's a polar solvent, it'll support our charge. However, ammonia is the weaker acid, so it doesn't reprotonate the alkyne. The other thing we can use is a reversible reaction. An irreversible reaction. If we had something like an sp3 hybridized anion here, in this case, we have a lithium supporting that negative charge on the carbon, it can then deprotonate and generate alkane. Now, it is technically a reversible reaction. However, this butane can boil out of the reaction, making it an irreversible reaction. So if you have no more of this weaker acid in your system, it becomes irreversible. So now that we have that anion there, and it's a nice stable anion, we actually is still a very strong base. It's not as strong a base as our butyl lithium here, but it acts as a nucleophile, and we can use that for nucleophilic attack. So we can attack any carbon that is either partially positive or has a good leaving group and generate a new, more complex carbon skeleton. So let's look at that. So one of the things we can do is we can actually attack a carbonyl. So we can attack a carbonyl, and that would generate an alcohol. And it could be secondary, tertiary, or primary, depending on what kind of carbonyl compound you start with. The other thing you can do, and so that would generate your alcohol here after protonation. So what would that reaction look like? Well, we'd start with acetylene, which is a gas. We'd bubble it through our sodium amide solution here to generate our anion. Then we would add our carbonyl compound. In this case, we're adding a formaldehyde. And in that case, because it's formaldehyde, remember when we attack, when is our next test? Oh, that's on. Our next test is on December 2nd. So it's on Canvas as well. All right. So when we have our anion here, it will act as a good nucleophile and attack here. And in the case of formaldehyde, it's going to generate a primary alcohol. If we use a substituted formaldehyde, like something with an R group on there, we would get a secondary alcohol after protonation. And if we used a ketone, we would get a tertiary alcohol from that. So it does the same kind of reactions that we would see that. But we always have to add something in there to protonate our alcohol species. Typically takes a little bit of acid. Okay, so that's one thing we can do with acetylene once we have it. We can deprotonate that terminal alkyne. Now notice these all have to have an alkyne with a hydrogen on them. So it has to be the end of a chain, or it has to be acetylene itself. Acetylene is just the alkene by itself, alkyne by itself. Sorry, I keep getting that wrong. Okay, so how do we form alkynes? Okay, well, one of the cool things is we can use a very strong base, and we can do a dehydrohalogenation just like we did alkenes, but we have to have 2 halogens and 2 hydrogens on those carbons to generate that second pi bond. So instead of just having a mono halo hydrocarbon, which you can only make an alkene from, if you had a dihalo, and they can be on adjacent carbons or on the same carbon, and with a strong base like sodium amide, butyl lithium, or some nitrogen, this is also a nitrogen anion reagent we'll get to next semester, we can dehydrohalogenate the first side, dehydrohalogenate the second side, and form the alkyne. Okay. So we would do the same thing here. We would dehydrohalogenate this side and then that side to generate our alkyne again. Okay, so now we can make alkynes too. Okay, so the mechanism is like you would see in a regular dehydrohalogenation of an alkene. They tend to run as E2 reactions. We have a strong base come in, start tugging on our hydrogen, then those electrons kick in, and then it kicks the electrons from the halide out. Okay, so if you only had one equivalent of base, it could stop at this thing, at this section. And in this particular one, we're making the Z isomer because of the location of the bromine and these R groups. These R groups right here are trying to be, notice these R groups are anti to each other. And when these R groups are anti to each other, they will make our trans isomer, or our Z isomer here. Now, the second step happens where the bromine comes in, and because these are anti to each other here, that comes in and deprotonates this, the electrons kick in, the bromine kicks out, and we generate our alkyne. Okay. Now, the E2 reaction always works faster when your hydrogen and your leaving group are anti to each other, because that means it's easier for the electrons to kick in and then kick out the leaving group. So that means this second reaction happens also very quickly, and we generate our alkyne. However, let's say you had a different isomer and you actually had our R groups in the Gauss configuration. What can happen is it'll still do that first E2 reaction, but it'll generate the cis isomer or the Z isomer here. I'm sorry, E isomer here. And that means that we have to actually take it as a coplanar deprotonation. Remember when we had those alkenes where we had to have them in the coplanar or in the anti. In the coplanar, it's a slower reaction, but it does yield the same product. So both of them happen in the reaction. It's just you might have to wait a little while for all of this E product to transfer. Okay. So that's how we can make alkynes. Now, once we have alkynes, they do a lot of the same reactions that the alkenes do. So we can add acid across it. And when we add acid across it, it's going to add across in a fashion where the hydrogen goes on the one side and the halogen will go on the other side. And it follows Markovnikov's rule. So when you have a terminal alkyne, the hydrogen will always go on the side where the hydrogen is, and the bromine or the chlorine will add to the other side. Okay. When you have an internal alkene, it's very hard to tell the difference because there is not as much specificity. So in this case here, we have the alkyne at the end of the chain, right here, giving us our major product as our one equivalent of the acid adds across the double bond, giving us our bromoalkene. Now, if you add a second equivalent, it's going to do it again. So, but if you own only one equivalent of this, it'll add once to give you that product. Okay. So, and the reason that we see it follow Markovnikov's rule is it does the same thing. It does actually form a carbocation. And in this case, it's an allylic, a vinylic carbocation, so it doesn't rearrange. It'll just stay in that one position and add with the halogen at the end of the reaction. Okay. So an alternative way to do that would to think of if you had two equivalents of it locating itself and forming an interesting transition state, it would give us the same Markovnikov's rule product. But I think this is the much more easier to remember mechanism. Okay. Now, like I said, if you have one equivalent, it'll stop at the alkene. If you have a second equivalent, it's going to add again across the double bond, and it will add across the double bond in Markovnikov's fashion. What that means is you're going to have two halogens on the same carbon, and they're going to be the one carbon in from the end. Okay. So let's see if we can do that addition across an internal one and see what the products might be here. So we have a CH3 on either end of here. And if we do our first addition of hydrogen, we're going to form that vinylic carbocation, which is then going to react with our bromine here. And then we have our second equivalent come in here and start to interact and add that hydrogen to that system. Okay. Now, you're going to think, okay, well, which way is it going to go? I mean, those carbocations will be like the same, won't they? They'll both be tertiary carbocations. Well, not exactly, because if you just form the carbocation right here, we actually can form either carbocation. It can form on the secondary over here, or technically this is a secondary because there's two carbons here. So you can form either one, but which one's more stable? Which one's going to give you your major product? Turns out carbocation right here is stabilized by the fact that these lone pair from the bromine can come in here, and we have a resonance contributor. that stabilizes that positive charge and pulls that positive charge out to this bromine. So now we actually have the carbocation on the bromine center is the more stable, more thermodynamically stable, and therefore yields the product again as a dibromo compound where they're on the same carbon. And that's called a geminal. Geminal dibromide is when they're on the same carbon. And if they're one carbon, if they're next to each other on carbons, that's called vicinal. So vicinal and geminal. And that's in the nomenclature chapter, by the way. All right, so we can add HBr across there just like that. But the bromination of an alkane is anti-Markovnikov. The hydroboronation, when we're adding acid across there, it's Markovnikov. The bromination adds two bromines to it and therefore isn't anti or pro Markovnikov because it is, it adds, there's no hydrogen there. Does that answer your question? So this is adding acid across the double bond. So now let's go and add a halogen across the double bond and see how that's different. Okay, so just like in an alkene, we're going to add one halogen to each side. And if we have two equivalents of halogen, what we're going to end up with is a tetrahalo compound here, where all four halogens are residing on the two carbons that made your triple bond. Okay. So let's see if we add just one equivalent, we can actually stop it, but there is going to be regioselectivity here. The making the, where the bromines are added opposite each other, the E configuration here, is more thermodynamically stable than adding them cis to each other. So we actually end up with a major product being the bromines trans to each other, not cis to each other, giving us our E configuration in our final product. However, if you then add another equivalent of bromine, it's going to, of course, add two bromines to that, and we get back to our tetrabromo compound here. Okay. So, and this works equally well with chlorine or bromine to give us our tetrabromo or our tetrachloro compound. Okay, so what's the next reaction we can do? Well, we can do oxidations. Let's do a reduction. Okay, so we're going to reduce alkynes. And alkynes, just like alkenes, are reduced easily with the hydrogen and platinum or palladium or nickel catalyst here. It's that catalytic hydrogenation reaction. And it adds, the first equivalent is going to add cis, because of course you have to sit on the surface of the material, but you just formed an alkene, okay? That alkene is still reactive to the reaction conditions, so you're going to reduce it down always to the alkyne. Oh, why am I getting that wrong today? You're going to reduce it all the way down to the alkane. And it doesn't stop. You can't just add one equivalent of hydrogen and try to make it stop at the alkene. It won't, okay? So what we do is we deactivate the catalyst. It's called poisoning the catalyst with lead and barium sulfate. And this is called Lindlar's catalyst, okay? This is the only way we can stop that addition of hydrogen across both of the pi bonds. And when we use Lindlar's catalyst, we also get that syn addition because we're still doing it at the surface of the metal. However, by adding the lead and the barium to it, it deactivates it enough so it can't reduce down alkenes. And therefore we stop at the alkene where the hydrogens are added cis. Okay, so it's still a cis addition that we saw in the alkenes, but we can stop to give us our cis alkene as well. Excuse me. Okay, but okay, so we can get all the way down to an alkane. We can get down to a cis-based alkene. Can we get to a trans-based alkene? And we can, but we have to change the mechanism, okay? So when we change the mechanism, we can do what we call a dissolving metal reduction. And this is literally take sodium metal in ammonia, and the metal will slowly dissolve, creating a salt, and will slowly create the transalkene, okay? So because it does the transalkene, because of the mechanism, we don't get syn addition, we get anti-addition from the system, because we must be forming something else other than just adding across that double bond. And in this case, we're going to be forming a carbanion, or a negative charge on the carbon. Okay, so sodium is a very reactive metal. It has one electron in its outer s orbital, and it really wants to give it up and become sodium plus one. Okay, so in this case, it has that one electron, and it's going to donate it to the pi cloud of, I'm sorry, not pi cloud, the triple bond here, and generate a radical anion. This says cation on the slide. It's a radical anion. Okay. And for stability's sake, the R groups are going to be trans to each other. We have an anion at one side and a radical on the other side. Okay. So now this is the key on why this adds anti. Okay. Because that single electron transfer generates that radical anion. Okay, and that radical anion is stabilized by having this sodium here. Okay, so now we have a nucleophile. The only thing this nucleophile has to attack is the hydrogen on the ammonia. Okay, so when it does this, it attacks the hydrogen on the ammonia, leaving us with this alkenyl radical and our sodium amide ion. So now your sodium amide and your amide ion and your sodium ion float away. Okay, we don't need them anymore. Okay, but we still have a radical. Okay, well, we need a second equivalent of the sodium to transfer its single electron in that s orbital to give us our anion again. And notice this anion, because the R groups are trans for stability here, we're going to end up adding that hydrogen trans to the first hydrogen. Okay, so what we end up getting is we have the formation of our anion first. It's now our nucleophile. It has to abstract the hydrogen from the only place it can, which is the ammonia, generating another equivalent of the amide ion, and it's counterbalanced by the sodium ion here. And so in the dissolving metal reduction, we get the transalkene, and then it stops. Okay, so we can get all the way to an alkane. We can use a poison catalyst to get to the cis-alkene, and we can use the dissolving metal reduction to get to the transalkene. Okay, so this is all about that selectivity of reagent to get to different things from the same substrate. Okay, so we've done adding acid, we've done adding halogens, we've done reduction. Let's go ahead and do a hydration. Just like with adding sulfuric acid and to generate an alcohol, we generate that as an intermediate, but it actually rearranges. Okay, so if we have an alkyne right here, we're going to add water across that double bond, generating our intermediate here. Okay, so look, our hydrogen added here and our OH added here. And then it creates what we call an enol. Okay, so that's an alkene and an alcohol at the same carbon, so it's enol that we learned in nomenclature. But enols aren't very stable. What they do is they rearrange to form carbonyl compounds because the carbonyl is more stable. So what they do is they transfer a proton over to the next carbon and generate a carbonyl. This is the much more stable form of this. Next semester, we're going to learn about enol keto tautomerism and how that helps us. But in this case here, we've added one equivalent of water. It goes to the enol form, which then rapidly converts to the ketone, and then the reaction stops. It's stable as the ketone. So we can take an internal alkene and we'll get our ketone. Now, it's not really selective inside there as to which carbon it goes to. So hopefully you're using a symmetrical alkyne, or you'll get, in fact, if it oxidizes here or here, it'll give you the same product in this one. So, but if you had them unequal on these sides, you would actually get two products. What happens if you have it with a terminal alkyne? Okay, because of the addition here, this being the more stable carbocation right here, we actually end up getting our ketone on the internal carbon. We can't tell the difference. There is no better stability on either one of these carbons because of the, they would both be secondary. Here we have a choice. We have a secondary or a primary carbocation, and therefore it's going to wind up on the secondary carbocation, giving us a terminal methyl ketone. So your terminal alkenes, kynes, give terminal methyl ketones. Okay. So, and then there's this possible mechanism I'm not going to go through because it's still up for debate. Okay. And again, the reason that this enol is not isolable is because it rapidly undergoes this exchange. And this exchange can happen in acid or in base. In the case of this, because we're using the sulfuric acid and the mercury here, it actually is doing in an acidic medium, and therefore what we end up doing is transferring a proton to our from our acid to, whoa, where do you go? And transferring a proton from our acid to our alkene, generating our carbocation. Whoa. And then that, of course, rapidly forms our carbonyl compound, and then our base can come in and give us our ketone. But that's the most important part there. Oh, darn it. All right, we're right here at 10:52. So what I'm going to do is I'm going to go ahead and stop here. We have 3 slides left, and I'll do those 3 slides at the beginning of chapter 9. But we have the boron reaction and the ozonolysis and the permanganate. So yeah, I'll do these at the end of, I'm at the beginning of class on Monday. Note there is a Cat's Web tutoring today, 12 to 2. Okay. All right, I'm going to stop recording. If you want to hang around and ask a question, please do. And if you have to go, go be safe, and I'll see you on Monday.